All right, so this lecture will be on the Navier-Stokes equations. So to kind of pique your interest, the equation that we're going to talk about in this lecture is if you can prove that smooth solutions exist for it, you get $1 million. I'm not even joking. Someone has set aside $1 million to prove that the fundamental equation of fluid mechanics has smooth solutions. So yeah, pay attention. Um, but like I said in the first lecture, if you end up proving that, you have to cut me in, okay? Because I'm your pro. All right, so Navier-Stokes equations. I'll review what we did last lecture first. So last lecture was about acceleration and the material derivative. Okay, so the material derivative, the core idea is if you have some Eulerian field, which again, an Eulerian field means it's kind of we're watching a fixed point in space, or we're watching a fixed space. If we have some Eulerian field and we take this material derivative of that field, you get a Lagrangian perspective. So you get the time rate of change of that quantity following a fluid parcel. So that's the expression for it there. It basically tells us that the total rate of change the parcel feels per unit time as it moves in our flow field is the local rate of change of the Eulerian flow field plus the local rate of change per unit space times how much space you moved through. So that's the entire rate of change you get. It comes from the chain rule in calculus. And a special case in the material derivative is if we take that material derivative of the velocity field, we get an acceleration. So you get the acceleration of a fluid parcel following it, which is a Lagrangian perspective. So this is the general expression here for the material derivative operator. This is the last lecture of Module 2. So the lecture later today, we're going to start Module 3. So Module 2 has been all about forces in fluid motion. So we've kind of zoomed in and analyze like fluid parcels in the same way that we would analyze things in solid mechanics or your mods class. So this is the last lecture of that. And what we're basically going to do is write F equals ma for a fluid. So F equals ma for a fluid is a relatively complicated equation, but we've derived basically all the terms in that equation at this point in Module 2. So we're going to put it together because it's a very important equation. And then later on in Module 3, so your next lecture, we're going to start looking at dimensional analysis. So it's going to be a pretty different field to what we've been doing so far in the course, but equally useful. So the learning objectives for today are just to summarize Module 2, to assemble the Navier-Stokes equations, and to interpret the different terms inside the Navier-Stokes equations. Are there any questions before I begin? Okay, let's get started. So let's kind of, on our way to assembling the Navier-Stokes equations, let's review the forces on a fluid element that we've talked about so far in the course. Okay. So we have some fluid element here. A fluid element, you can think of it same thing as a fluid parcel. Okay. So there are two types of forces that we've actually talked about. We haven't really defined these yet, but you'll see that the forces that we've talked about are in these categories. So the first category is going to be surface forces. And they're called surface forces because they act on the surface of our fluid parcel. And the second type is body forces. And they're called body forces because they kind of act on the bulk of our fluid parcel. So the surface forces we talked about. We talked about two surface forces. Does anyone have an idea of which forces that we talked about could be considered forces that act on the surface of a fluid parcel? Yes? Exactly, yes. We talked about friction and pressure. So those are both forces that act on the surface of a fluid parcel. Does someone else have their hand up over here? Is that what you're going to say? Okay. So we have a normal force, just like in solid mechanics. You have your surface of your element. You have a normal force. So that normal force is due to pressure. We have a tangential force, aka shear force, and that's due to friction. And we call friction forces in fluids viscous forces. So those are the two types of surface forces we talked about. We did talk about one type of body force so far. Does someone have an idea of which body force we talked about? Volumetric strain. So that's more of like that's not really a force. It's more of like, it leads to conservation of mass. But that's a good answer. Anyone else? Yep. Force due to acceleration. That's a good one. Yeah. So force due to acceleration. So a special case of that could be gravity. So in particular, we talked about the force due to gravity. So aka the weight of a fluid element. Like Aaron said, so that acceleration force can actually be grouped into that gravity weight term because it acts on the entire body of our fluid element. Okay, so these are body forces, but there are other examples of body forces that we're not going to analyze, I guess, quantitatively in this class, but they're interesting to think about. So other body forces that act on some fluids are electromagnetism. So if we have some sort of charged fluid or a fluid with magnetic particles suspended in it, those forces would come into play as a body force in our governing equation. And also the Coriolis force. So the Coriolis force is about rotation. You might remember that from your solid mechanics or dynamics class. Um, like for example, a projectile along the Earth, as the Earth rotates, the Coriolis rotation is accounted for in the coordinate frame. But on a fluid, it can produce a force on different parts of our fluid. So that's the Coriolis force. Um, it sounds niche, but it actually has quite large practical implications. So the Coriolis force is the reason that um, storms in the northern and southern hemisphere rotate in different directions. So I have some videos that I'm going to show about that. But we're not going to analyze this quantitatively because for the most part, these Coriolis forces apply mostly on very large scales, so the atmospheric scale fluids. So for the most part, engineers don't really worry about the Coriolis force on, say, something like a fluid in the HVAC system in a building, for example. Okay, so I'll first talk about the Coriolis effect. So this is a video by the Royal Met Society. Believe it or not, this video is meant for kids. So I guess the British kids must be a lot smarter because it's pretty complicated.
The water flows from where there is more to where there is less, and the water levels out. So, in the atmosphere, if there is more air in one place, high pressure, and less elsewhere, low pressure, the wind should move air from high to low and level the pressure out. But this doesn't happen. The wind blows along the pressure contours in circles around high and low pressure areas. Why? Imagine you are standing at the equator. In the course of a day, you travel about 40,000 kilometres, a speed of about 1,670 kilometres per hour. You don't notice it because the air around you is also travelling at the same speed, so there's no wind. On the other hand, at a pole, over the course of a day, you would stay in the same spot, but just turn 360 degrees. You and the air around you aren't travelling at any speed at all. So if fast-moving air from the equator is pulled towards the poles, it is travelling faster than the ground underneath it, and it overtakes it. On the other hand, slow, polar air gets left behind if it's pulled towards the tropics. So any air trying to move south or north can't travel in a straight line, but ends up moving progressively towards the east or west. More generally, the Coriolis effect tells us that moving objects on the surface of the Earth are always deflected to the right in the northern hemisphere and to the left in the southern hemisphere. It's all due to having to consider what the Earth's rotation looks like to someone on the ground. To understand the local effect of the Earth's rotation, you have to split it into components around the local vertical and the local north. To people standing in different places, north and vertical could mean different directions. At the equator, the component of the Earth's rotation about the local vertical is 0. That's why you never get tropical cyclones near the equator. Think of a low-pressure area in the northern hemisphere. The pressure gradient pulls air in from the surrounding higher pressure areas. Air coming into it from the north is deflected to the right, to the west. Air coming in from the south is also deflected to the right, to the east. Eventually, the Coriolis force balances the pressure gradient, and you end up with circular motion. In the northern hemisphere.
So I guess what they're saying there is the pressure gradient force, which we talked about, can balance this Coriolis force. That would be kind of the governing equation for an atmospheric scale fluid for some cases.
You end up with circular motion. In the northern hemisphere, the wind blows around a low-pressure system in an anti-clockwise direction. So why do weather systems rotate in opposite directions in the southern and northern hemispheres? Imagine looking at the rotating Earth from space. If you look down at a dot on the surface of the Earth from the North Pole, it looks like it is rotating anti-clockwise. If you look down from the South Pole, it's rotating clockwise. Think of a low-pressure area in the southern hemisphere. Air coming into it from the north is deflected to the left, to the east. Air coming in from the south is deflected to the west. You get clockwise spinning where they meet. That is why storms rotate in an anti-clockwise direction in the northern hemisphere, but rotate clockwise in the southern hemisphere. This is the Coriolis effect.
All right, so I also find that video a little bit confusing, but basically the interesting part is that the Coriolis effect produces this rotation of tropical storms in different directions, and the different kind of coordinate frames in the different hemispheres are the reason that they rotate in the different directions. So that's just kind of a fun fact. The electromagnetism, like an example of that is if you've heard of ferrofluids. I do have a short video I can show as well. So ferrofluids are like fluids that you suspend magnetic particles in. So these particles, I guess, create kind of a body force within the fluid. So if those particles are within a magnetic field, that force is then transferred into the fluid.
Very weird liquid, this.
Yeah, so
On the scale of 1 ton of weirdness, this comes about 433.
So this is what I guess fluid looks like when it has that magnetic body force within it.
Is it the blood of some strange machine, you ask? Do you ask that? I asked that.
It's kind of, there's not many applications in
And the
engineering
liquid
like this,
is rare.
but some niche applications you'll get these kind of
That's 'cause
magnetic
this liquid's
forces.
got
So for example, if you're designing like a system with plasma inside it, like say a nuclear fusion reactor, which is a big area of research right now, the plasma is kind of like a fluid, but it's within a magnetic field. So you have to account for that force when you're doing the fluid equation of motion. So in simulating those flows, you have to have that force in your simulations. So those are some other body forces, but the one we're going to deal with in this course is, I would say, been the most boring one, which is just gravity/weight. So it's just the weight of our fluid element. Okay, so let's put together Newton's second law. Okay. So we'll start with F equals ma. And Newton's second law is basically conservation of momentum. So the forces that we've talked about above were force due to gravity plus the force due to pressure plus the force due to friction. We'll replace m with rho v. For a small fluid element, we'll say dv, so rho dva. Just a reminder, gravity is a body force. And these two are surface forces. We also did talk about surface tension, but we're going to neglect surface tension in this analysis. So this is the equation of motion like within a fluid, not at an interface. So neglect surface tension. I'm going to start substituting the different forms for these terms that we've derived. Okay, so the gravity is going to be rho dv times our gravity vector. So for example, if you define your coordinate system with y positive upward, the gravity vector would be like 0, negative g, 0. So that's why I haven't put the negative sign there. So the gravity vector should account for that, I guess, direction of which the gravity field is pointing. So rho dvg. We derive the force due to pressure is negative of the pressure gradient times dv. Force due to friction, we actually haven't derived this term. I'm going to leave it in this line as lowercase f friction dv, where that f friction is basically small f friction is big F friction divided by dv. Okay, rho dv. And then we have our acceleration here on the right-hand side. So the acceleration, we just learned last lecture how to compute the acceleration for a fluid parcel, and that's the material derivative of velocity. So dv by dt, and that's the material derivative. Don't worry too much about this lowercase f friction thing. It's not something you have to worry about. So we're going to cancel out our dv's. And then we'll write the equation. So the equation is rho dv by dt is negative pressure gradient. So that friction, lowercase friction term, we're not going to derive why it's this way in this course. I'll just give you what that term actually is. So it's mu nabla squared of v. So nabla squared is the, sorry, that should just be a regular v. Okay, so I'm, just to be clear, I'm not, the v's with the ticks are the volume, so dv, and this v is the vector velocity field. Okay, so the term of that, or the form of that, you don't need to worry about the derivation for this course, plus the gravity. So I'll make, okay, so here's our equation. It's normally written like this. It's kind of A equals, sort of like MA equals summation of forces. So it's just flipped, left and right hand. But basically these are our forces. And this is like mass times acceleration. So all this is summation of forces is MA for a fluid element. So here we have dv by dt, again, is the material derivative. That nabla P is the force due to pressure. This term mu nabla squared V is the viscous force. So that nabla squared is the Laplacian. So in the taking the Laplacian, what you do is you kind of increase the rank. So you increase the rank and then decrease the rank. So you get, if you take the Laplacian of a vector, you get a vector back. The last term is body forces. In this case, all we've considered is the gravity body force. But in the general case, this is sometimes left just as kind of some general body force term that gravity can be included in. So I'm going to write the lecture numbers here in red. So the material derivative we did last class, that was lecture 15. This pressure force, the form of that term we derived in lecture 5. The viscous force, we didn't derive this, but we talked about a special case of this when this force only occurs in one direction, which is the case for the Couette flow. So we did that in lecture 11. And this body force term we derived in lecture 6. So we have basically derived all these terms except the viscous force. You'll just have to trust me and that you don't want to see me derive that. Okay. So this is the Navier-Stokes equation right here. It's basically conservation of momentum, aka Newton's second law for a fluid parcel. The other equation that accompanies this is conservation of mass for a fluid parcel. So the second one is the divergence of the velocity field is 0. So the left-hand side equation is conservation of momentum. This one here is conservation of mass. Together, these two equations govern any fluid. So the fluid of air in this room, the fluid like of the atmospheric scale flows. This is a very, very general equation. And it's the main equation that's solved using CFD. So it's solved using a computer. So for example, all the CFD software packages that you might have heard of, they're basically just different numerical ways of solving this. It's quite a difficult equation to solve. I guess sorry, I didn't write the conservation of mass is about the volumetric strain. Okay, so that was lecture 14. So these equations together are called the Navier-Stokes equation. Basically, all it is conservation of mass, conservation of momentum. But when you write it for something that deforms continuously under a shear stress, aka fluid, they end up looking like this. And this even here is a special case of more general forms, but this is the most common case that we use in engineering. Are there any questions about this equation or these two equations? So this is what we've basically been building towards in module 2. So we've looked at some special cases of this equation, right? So hydrostatics, for example, is the case where a lot of these terms cancel out and we just have pressure gradient balanced with the gravitational force. In the rigid body motion acceleration case, we replace the acceleration with kind of just one acceleration because there's one acceleration felt by all of the fluid molecule, all the fluid parcels, they all feel the same acceleration. So that's how you get that equation. We haven't studied, I guess, the exact behavior of this viscous term, but we have looked at the effects produced by it. So like the boundary layers, the shear stress at the wall, that's all produced by this viscous term, the shear stress in our fluid. So any questions about this? Okay. So I'll make some comments now. actually gonna move this. Okay, so what we have here is the unsteady, incompressible, Navier-Stokes equations for Newtonian fluid. Newtonian fluid meaning we have a linear relationship between shear stress and shear strain rate. So this is what the viscosity term looks like for a Newtonian fluid here. So if you have a compressible flow, these equations look different. If you have a steady flow, you can cancel out some of the terms in this equation. But I'm going to just leave it like this in general. Okay. So someone want to take a guess at, so these are vector equations, right? So how many, I guess, different equations if we have a 3D unsteady flow, how many different equations do we actually have here? Let's take a guess. Yep. X, Y, Z in time, that's a good guess. Yeah, so that would be our velocity field depends on X, Y, Z in time. But we don't really have, so we would have X, Y, Z components of this momentum equation. So you know F equals ma is a vector equation. So this has X, Y, and Z components. So that's 3 equations there. And on the right-hand side, this conservation of mass equation. How many equations is that? We talked about this 2 lectures ago. 1. Yeah, 1. So it's just one equation. It's a scalar equation. So the divergence of the velocity field produces a scalar. So this is just one scalar equation. Okay, so we have 4 equations. So 3 conservation of momentum components and 1 conservation of mass. Okay, so 4 equations. And how many unknowns do we have in these equations? So assuming we know the fluid properties like density and viscosity, how many unknowns are formed in these equations? How many unknowns do you want there to be, seeing as how we have 4 equations? 4, right? That's good. And if we have additional unknowns, if we have more unknowns than equations, we're basically missing an equation, right? So yeah, we have 4 unknowns. And those unknowns are the velocity components, UVW, and the pressure field. So we have 4 equations, 4 unknowns. The comment is what I mentioned. So this is an equation that's actually studied heavily by mathematicians. So you get $1 million if you can prove smooth solution always exists. So they put aside they announced this prize of $1 million in the year 2000, and no one has done it yet. So, yeah, so it's something I guess they're working on. I think my understanding is they proved it for 2D, but no one's done it for 3D. So it's unfortunate that they haven't proved that smooth solutions always exist, but we have to solve it because we're engineers. So we have to solve it because this is governing equation for our physical systems. So don't worry too much about that. Don't let that keep you up at night that they haven't proved that smooth solutions always exist yet. Yes, please. Smooth in the mathematical sense. So without discontinuities. Not considering like the special cases of discontinuities we talked about, like free surfaces and stuff like that. So they haven't actually proved that given a set of initial conditions, this equation will produce a good solution that we can use. They haven't proved it, but I guess we haven't observed that it doesn't happen. So we don't worry about that. Any other questions about that? You can look it up. So those are called the millennium problems. And there's other math problems too, but this is probably one of the more applied ones. The other comment is more to come in fluids too. So in fluids too, you'll learn how to manipulate this equation and solve it for, integrate it for some special cases. So that you can derive, for example, the linear velocity profile, you can derive that using this equation. Or the expressions for the boundary layer thickness, the velocity profile and a boundary layer. All those arise as analytical solutions of this equation. We've seen some analytical solutions of this equation. For example, the hydrostatics, that was an analytical solution of this equation. But you'll do more of that in fluids too. The last comment I have is that whenever we study fluids, we are implicitly studying the effects produced by these equations. So whether you like it or not, there's a joke that experimental fluids people say, so the CFD people are always basically trying to solve these equations to some sort of precision. So that they kind of iterate like numerical methods to try and satisfy conservation of mass, conservation of momentum, which is these equations. The experimentalists, they have a different problem in that their equations are always solved perfectly because they're studying an experimental fluid, but it's harder to measure. So in CFD, you have access to all these quantities because you know the fields everywhere. So you can get whatever information you want, basically. But you can't really guarantee that the equations are always solved perfectly. The experimentalists, the equations are always solved perfectly for them, but then they have to figure out how to measure it. So that's the two kind of different approaches to studying the fluids. Okay, so that's the comments I have about that. I'm going to write out one component of the momentum equation just to show you what it looks like. So if we have V equals U I hat plus V j hat plus W k hat, these equations look like this. So the first one is continuity. Just partial U by partial X plus partial V by partial Y plus partial W by partial Z equals 0. So that, which is the volumetric strain rate for an incompressible fluid, is 0. So you kind of have conservation of volume. That just tells us that mass is conserved. So that's the first equation, the continuity equation. Then the momentum equations. Okay. So we have rho, I'll start with the left-hand side. So we have rho times the material derivative. Material derivative, the x component is partial u by partial t plus u by partial x plus v partial u partial y w partial u by partial z. Okay, that's the material derivative written out in its components. Again, this is just the x direction. These equations are available online if you want to, I guess, check this or look at the full form. But this is just one of the momentum equations. Equals x component to the pressure gradient plus mu. So that Laplacian term I haven't shown you what that produces yet, but it looks like this. So it's partial squared u, partial x squared, it's partial squared u by partial y squared, it's partial squared u by partial z squared. Rho gx. Okay, I'm going to go through actually and just change the color of what actually would change in each of these. So we're doing the x component. So we're considering on the top there u, because u is the x component of our velocity. And we're considering partial x here. And we're taking the Laplacian of the x component of our velocity. And that's all balanced by the pressure, by the gravity in the x direction. So the terms in red there, I'm just going to check that. The terms in red there are what would change if you wrote this in y. So if you do y, you replace the u's with v, and you replace this with y and replace that with y. So that's one of the momentum equations. I'm not going to write all of them out, but because in this course, we're not going to really go much from here, so there's not much point in writing them out. Are there any questions about that equation? So it's much more compact to write it in this sort of calculus vector notation form, right? So in particular, the thing that makes these equations so hard to solve and that produce so many not like all the turbulence, everything comes as a result of these equations. It all starts basically here, and then you can study how different things evolve as they propagate to these equations. So the hard part about these equations that produces things like turbulence is that um, they're chaotic. So that means that if you have a very small change in your initial conditions, you can get huge changes later on down the line. So they're very, very sensitive equations in terms of small changes can produce big changes in the result. So the hard part is basically here. So this is the nonlinear / hard part. And it's also the part that makes them expensive to solve, expensive computationally. So a lot of money is spent solving these equations every year. So that's the part that's responsible for a lot of it. And what that part comes from is it's actually the part of our material derivative. So this term in the material derivative, basically the term that you pick up, the change that you pick up moving through space times how fast you move through space, that is like kind of a nonlinear effect, and that makes these equations expensive. Any questions about that? I'm just going to finish off by reviewing the special cases we did. So special cases. I'll rewrite the equation just so we have it here. So that's the equation. So in hydrostatics, we said we said one, it's steady. Okay. let me just rewind for a second. I mentioned that some of the terms cancel out when we're steady, right? So steady means that partial whatever by partial t, there's no variation of our Eulerian field in time. So the only term that's actually partial by partial t is this first term in our momentum equation. Nothing in our continuity equation depends on time. Our momentum equation only has this term that depends on time. So these equations look almost identical for a steady flow, except that you don't have this partial by partial t term. You still have these and all the rest of it. So they're also pretty hard to solve for a steady flow because you still have all those nonlinear issues. You're just saying we're not going to evolve that in time. So these balances all still happen for a steady state flow. Anyways, so for hydrostatics, we said there's no motion, and we said that it's steady state. So we said there was 0 is negative. If you go back to the hydrostatics lecture, this is basically where we started. And in this case, we were able to derive an analytical solution. And the analytical solution for that, about basically rho g y, produces like the pressure on submerged bodies and manometry, all that. So that was lectures 6 to 8. The rigid body motion case. In rigid body motion, we didn't use the material derivative. We hadn't derived it yet, but that was okay because all the fluid experiences the same acceleration. So there's still no relative motion in our fluid, so there's no viscosity effects. Everything accelerates the same. So we can just replace the material derivative back with A. So that was rho A is negative pressure gradient plus rho G. Again, we had an analytical solution available, so I'm just going to put quotes there. That was lecture 9. In terms of what else we covered in this chapter, so effects produced by that term there, mu gradient squared V. So we didn't really study an analytical, I guess we studied one very, very special case of an analytical solution of this, where we had the linear velocity profile for a Couette flow. That's technically an analytical solution of this term. So that produces skin friction, boundary layers, lectures 11 to 13. For a special case, which was Couette flow. Analytical solution was available. So in fluids too, you'll see why that linear velocity profile was derived, but I can just explain it kind of in words. So the Couette flow case, what actually happened was, if you cancel out every single term in this equation, so if you say you have, the Couette flow case is only flow in the u direction. The other velocity components are 0. So what that means is that also you say it's steady case. So that means that this term goes away. If you say it's fully developed, there's no gradients in the x direction. So that means this term, the v is 0, so that goes away. The no flow in the z direction, so that goes away. You say there's no balancing pressure gradient. Again, there's fully developed, so the x gradient goes away, and you say it's 2D, so the z goes away. and there's no gravity. So the only term you're left with is partial squared u by partial y squared times mu equals 0. So that's just basically the second derivative of something equals 0. So if you integrate that twice, you get a linear profile. So that's why we got the linear velocity profile. Again, you're not going to be asked to do that in this class, but in fluids 2, you'll see exactly how to do that. But basically, that's why you get a linear velocity profile. Any questions about this? This is basically a summary of module 2. So we've been building a module 2 towards this equation, and now we're kind of looking back and seeing all the things we studied that were produced by this equation. Okay, so I think that's all I want to cover today. So are there any questions? If there's any questions, let me know. I'll see you guys later today, but thanks everyone.